Well, hello everyone. My name is Carlos Bilbao. I work for DigitalOcean. I have stickers and swag for anyone interested. And today I'm going to talk about integrating confidential computing into the cloud. So for a little bit of background, in the past we worked on a threat model for confidential computing, which fundamentally alters our long-standing assumptions of who are the attackers and what can you trust and what can you not trust. I will go through the threat model a little bit. But the idea of confidential computing is that you don't need to trust the host. So that makes cloud operations more complex, but it also brings in new types of clients, whether it is highly regulated, compliance-heavy industries like government or healthcare, proprietary software like high-frequency trading, or privacy-first applications, people that are paranoid about developers with keys, that sort of stuff. So until recently, confidential computing was theoretical, but it is not theory anymore. There are commercially available products now. But in this talk, I wanted to discuss a bit more of from a broader perspective of the open source community as a whole, some questions that remain open or some things we should think about. So this is the classical threat model of a guest virtual machine. Everything in green is the TCP that you trust. And so there are certain attack vectors, whether things that come from the guest user space or some external attack vectors, whether from USB or the network, that sort of thing. And then, well, in the case of x86, you have ring 3 and ring 0, but everything is trusted. And with confidential computing, the difference is there is much less green. So that's good, less smaller attack surface. The way you are able to have this smaller TCP is by having this thing that I call the CoCo platform security manager. That can be hardware, that can be software. It depends on the company, it depends on the hardware manufacturer. They go for different approaches. But at the end of the day, conceptually, you have this component that allows you to establish a root of trust. And that way, you don't need to trust the host. And so just like there is less green, there's also more red, because there are new attack vectors. Anything that has to do with the execution context of the VM or its memory, constructs that are shared, basically, page tables, registers, that sort of thing. So how do we change the cloud to make this make sense? So the first thing that needs to change is the boot. So this is a secure boot process. Do me a favor and ignore the component on the left, the orange one. So if you start looking at secure boot from the firmware, you have a database with the signatures and another database with the revoked signatures. That's all on non-volatile firmware memory that the OEM installs and includes the keys that you can use, the firmware can use to verify the shim, which is a small pre-bootloader. So it will verify it. It will put it in the VRAM and jump to it. And so then that same way with another cryptographic key, you are able to verify the bootloader. And so you jump from one stage to the next until you finish this chain of trust all the way to the secure VM guest. So the component that I ask you to ignore, the orange part on the left, is Secure VM Service Module, SVSM. So that's a way that you can achieve confidential computing by having this privileged software running in a special hardware mode. In the case of AMD, it's VMPL0. So my point is that secure boot doesn't change as much, but you tweak it a little bit so that the chain of trust include what you need to include in order for confidential computing to make sense. So, well, you use a TPM. In the case of this VSM, for example, you can use a virtual TPM where you have PCR registers. In this case, the ones that you use to generate the hash on secure boot are the static root of trust measurements. But you go through every stage, and you include the cryptographic digest. So, and then finally, you get to the VM, and you close the circle by attesting the secure module or whichever software you have used to allow for confidential computing. You close the circle, and you also have to accept and validate the memory pages from the guest side. And so this thing on top is another way to do the same thing, or accomplish confidential computing, but this is the way that Microsoft does it with LBVS. So the difference is that they start on the firmware, and then before they launch the guest, they have this component, which is like a paravisor. It's a small version of the Linux kernel, also running in a special hardware mode. The advantage of this approach, as opposed to using SVSM, is that it's hardware agnostic. But by the same token, there are other drawbacks. For example, even if it's small, it's a Linux kernel. It's still much larger than SVSM. That it could be written in Rust, for example. So my point is not that there is a better design than other design. My point is that there are many designs with a lot of pros and cons, and different hardware vendors, you will ask them, and they will tell you, well, we have this, we have that, so which one's better? So from the perspective of a cloud provider, the point that I would like to bring up is that there isn't a simple way to understand these trade-offs and different approaches. What are the pros and cons of these different flavors of confidential computing? In terms of performance for the cloud, there's a couple of things to keep in mind. I used to work in the hardware industry, but now that I work for a cloud provider, I started to wonder how certain things may actually impact our day-to-day operations. So a boot time penalty, I thought there was going to be penalty for encrypting and decrypting the memory pages, but in reality that happens in line in the memory controller. Depending on how cache resident a workload is, there may be some impact, but the real penalty comes from the process that I mentioned before of accepting the pages. So one solution that I will propose is to pre-accept those pages. So before you get to the guest VM that has to accept those pages by performing a hypercall, you do a VM stop, and all of that, you pre-accept those pages all at once before you get to that point. There is runtime latency, because you have intermediate buffers with SMP or with TDX. And now hardware companies are working on different solutions for that. AMD recently released Trusted I/O. From scalability, there are also hardware limitations. So the hardware limitations don't include the entropy or running out of entropy. That's something that was discussed in the mailing list in length a couple of years ago. The real hardware limitation, for example, in the case of AMD, there is address space identifiers, ASIDs, and you set the number of those in the BIOS, so around 200. And once you get to that point, you cannot create more. Now, current CMP servers have hundreds of cores, and probably this trend will continue now that the Moore law is dead. So they will continue to increase the number of cores, and that's why I think it will be interesting to consider hybrid models. And what I mean by that is that right now, if you want to enable confidential computing, you set, for example, config SMP to yes, and that means the memory pages of the VMs go through confidential computing. But you are not able to create VMs that do that and VMs that don't do that. So with a hybrid model, you will be able still to create all the confidential computing pages that you wanted, but then on top of that, you will be able to create just regular VMs, so just so you don't waste those resources. I know there may be micro-architectural limitations to doing this, but just as a thought. Swap memory is another problem, because that memory, you take it to the disk, so you have to encrypt that disk as well. And finally, cloud providers really care a lot about SLA and SLO metrics, like the famous 4 nines, 99.99 of availability. And there's these contracts that they sign. And with confidential computing, I wonder how do these contracts change? Do they relax them? I know Google, with their confidential VMs, I don't think they relax these contracts. But I do wonder how do they reach the conclusion that the performance is not going to be impacted. So in that sense, I would say that maybe there's a different target audience, because when we think of cloud, we usually think of client-server applications that have peak times where quality of service is critical, and maybe applications that are more like HPC or scientific, even though they may suffer from NMIs or something like that. With confidential computing, they will be better suited to run under this type of threat model. Live migration is also really important in the cloud. You want to move VMs, say, for example, during maintenance, and you want to do this in a seamless way. So, for example, you want the IP to remain the same thanks to a virtual network or something like that. So the question of boot time penalty comes again. So you may think you don't need to worry about that because you can pre-attest another node, and then when you have to do live migration, you just go ahead and move the VM to that other node. But two things to that. First, in the cloud, sometimes there are emergencies. So you just don't know if when you get to the destination node, you're going to have to perform another live migration right away. So having a plan B helps, but you can only do that so many times. And then, well, in terms of the SVSM or the service module, it needs to also keep track of the change of states, just like QEMU does. So the reason why I say this is because with confidential computing, you don't trust the host. So when you migrate to another node, you have to make sure that the changes that were supposed to reach the other node have indeed reached the other node. And in terms of offline migration, where you basically shut down the VM and then migrate it, I don't think that's something supported, at least for AMD right now, but it will be nice in the future because we do need it in the cloud. Observability is another critical part of the cloud. You need to understand like the health of your fleet. You need to be able to detect abuse from clients and generate alerts. And confidential computing shouldn't affect it too much. I mean, you can still trace guest hypercalls. You still can trace the virtual driver, which, by the way, is confidential computing compliant. You can trace KVM IOCTOs. You can monitor the network traffic. The only thing I would say is that with trusted I/O, where you include confidential computing in the devices themselves, maybe you lose a little bit of visibility, and you end up with the same visibility as with DMA more or less. So I think there is like that friction we were talking about between performance and security and the isolation model being broken a little bit. I don't know if classical things like VMs or containers will be able to accommodate all these requirements at once. But yeah, that's something to consider. And then more of a future-oriented thing is in terms of cooperation, because it gets a little tricky. So we talk about we don't trust the host, so we want to harden the guests from malformed inputs or malicious inputs or from misconfigurations from the host. But at the same time, in the cloud, I think we should try to have more cooperation between the guest kernel and the host kernel. So the example I like to give is the semantic gap in the schedulers. You can have a guest scheduler that doesn't know the NUMA topology underneath, and you can have a host scheduler that doesn't know whether the guest acquired a lock. So Linux solves this with KVM paravirtualized locks, and this type of constructs will still work with confidential computing, but then other type of mechanisms of cooperation between both kernels that rely on shared memory will need to be changed in the kernel. And so the question comes up, like, what's the right balance? It's a little tricky from a security point of view because you don't trust this component, which is the host kernel, but at the same time, you want to cooperate with it to improve the performance. And the cloud is much behind from HPC, so there is a lot of room for improvement in that sense. And that's it. Yeah, I think I talked about a lot and quickly, but anyone has any questions? Oh, you can tell me, and then I'll repeat the question.
OK, so first of all, myself, I'm ED of the Confidential Computing Consortium. A number of things that you talk about, we would love to discuss more in that context. We have a Linux kernel SIG and some other places as well to do that. That's great. Some of the questions you had around debugging and observability are things that I've published on before as well. I'd love to chat about that. But these are all really important things, and I'm really glad that you're discussing them here. So it was just a yes, thank you.
Well, the question was thanking me for the presentation, so thank you back. Yeah, I mean, so I love confidential computing because we talked a lot today about how do we limit escalation attacks, but ultimately we need to agree that it's impossible. It's impossible for us to completely protect the kernel. So given that that's impossible for us to do, maybe it's worth considering the idea of what if we assume that it's untrusted. So that's what confidential computing does. And there is the performance overheads, and there's the complications of implementation and such. But I do see a lot of value in that. And this doesn't mean that you just don't trust the cloud provider. I mean, I work for a cloud provider. But it's more about even if the cloud provider is compromised, even if the attacker finds a way to escalate inside the kernel, the guest VM is still protected. Not protected availability-wise, because you can always pull the plug, but in its integrity and its availability of the data in use.
I have another question. I think the gentleman had one as well. I guess I have a hard to answer the question. Where my head goes from that is taking a step back and thinking about when you apply that to a cloud provider, and thinking about those threat models that you're kind of touching on, but like adding a little bit more to that. Are we considering scenarios where I have to assume that my cloud provider or the hypervisor that they're providing to me at this point is just flat
Yeah, that's the. Look, so the.
Then I've got to take the threat model of my cloud provider is adversarial to me and/or slash like is being, has a government that is compelling them to do something that is against my interest legally, therefore
Yeah.
I do so. If I can't take that off the table, what threats can I take off the table, right? Like what? There's lots of interesting
So.
technology pieces, but I go to that layer 8, 9, 10 problem of, well, hang on, what is the set of situations I'm trying to protect myself against?
So the question is like the idea that fundamentally this means that you cannot trust the cloud provider and like the implications of that, and the implications are deep. But I think like you bring up a very good point. Like you say, like what if the government like forces them to do it? Like what if they come and tell me to? So that's the thing about confidential computing is that it doesn't allow them, even if they want to. Because even if you, like as the cloud provider, are forced to give out this information, you can tell the government, sorry, I can't. Because the memory of these clients is encrypted hardware-wise, and if I try to tamper with it, then the memory is sealed with the TPM, with the virtual TPM, and if I try to tamper with it, that's going to be detected. So I'm actually really glad to be doing this presentation right now. If I have given this presentation a year or two ago, a lot of people were skeptical about whether this could be possible or not, but we have started to see commercially available options. So it is possible, but there are like hard questions in terms of performance and security still. Sorry, which one do you?
So can I respond to that a bit, which is that doesn't mean to say there aren't nation-state attacks that may be in scope, and generally the hardware providers don't say that long-term physical attacks are out of scope, but it does rule out a whole set of types of vulnerability or compromise and threat vectors. But of course, nation-states can usually find a way. Yeah, that's kind of thinking about it, right? Is like to your point, can I get into a state where the system is running safely and I can have confidence it is, and then if some, right, like it becomes a timing thing, maybe is kind of what you're talking about is, as long as the platform was trustworthy when I got up and operating and decrypted my sensitive information that is now only in memory, well now I've got fairly high confidence that the structure is set up such that it would be very difficult for them to get a memory dump and decrypt it and get my data. But I have to assume that the environment was cleared when I booted. What is the set of assumptions mechanisms
That's right.
to do exactly that? And you can do them at later times if you wish for certain parts of memory. And so I guess the thinking about like how do we think about how far that chain goes, right? Like given enough time, if I can upstream a hardware compromise, all that's wrong, right? Like I really want to this step discussions, some of which you've had and some of which I want to have more of. So
I saw you, no problem. I think he's next.
Oh, well, if I might speak towards nation-state threat actors, right? So out of the mouth of a nation-state exploit developer who shall not be named, right? The comment directly, last time we talked about sort of architectures like this was actually usability, which is, it's an interesting aspect of this to consider is how can confidential compute, which is this beautiful system, actually be applied in a consumer device context or in certain high security contexts where people may still want access to everyday applications like Signal or things like that. And speaking more generally or more technically, right, there's innumerable interconnections in computers, right? So whatever you're doing in the confidential compute environment still ostensibly has to, at the end of the day, talk to hardware devices and has to be communicated out of the confidential environment. It's not a perfect black box.
Right. So the point is that you cannot just isolate the confidential computing guest. Like, you still rely on the host for many things. Like, for example, set the time, or like when you receive inputs from the host in this threat model, those inputs are considered untrusted. So there's a couple of things you can do. You can harden the inputs, like to verify that it has a shape that looks good. You can also limit the attack that attack surface, that exposure, for example, by not letting the host send you any type of interruption. So there is like hardware mechanisms, restricted injection, where you only allow the host to send you certain type of interruptions. So I agree. Like it's an ocean of attack vectors, and and KVM and KMU, you cannot even trust them. So there are a lot of potential attack vectors that need to be considered. And that's a problem upstream, because you can find a security vulnerability and tell a maintainer, but the maintainer will tell you, what are you talking about? I don't do confidential computing. So that's why I made a point to mention that the Virt.io driver is confidential computing compliant, because they decided to accept patches that were bug fixes for this sort of thing, which not everyone has done right now. You had a question? So the point is that the value of open hardware like RISC-V in this context. So let me ask you something. Like for validating like memories, AMD has an x86 instruction. It's called pvalidate. Like how would RISC an open architecture, which I like, but how would that make it any better in that sense? Oh, okay. I see what you're saying. Like maybe they decide to put a backdoor in the hardware itself.
Or you go with the microcode confirmer, actually, which at least ARM is open sourcing, but AMD and Intel don't. So you've got a number of, so there's a bunch of analysis going on that I'd love to keep sharing.
It's a good point. Yeah, I mean, I'm European, and over there they love RISC-V. They're investing a lot of money on it, and I totally see the security value of doing so. Any other questions? All right, thank you.